you, organizers. Thank you. Thank you very much.
Thank you, ma'am, and thank you, sir, for your valuable time. And thank you, participants, for the knowledge shared with us. Now, let's resume towards our next invited talk. Our speaker is Chinmoy Saha. The title of the talk is Ultra Wideband Antennas for Diversified Application, a Journey for a Decade and Future Directions. The distinguished chair for the session is Dr. Thomasutty Matthew, Geetham University, Bangalore. I welcome you, sir. Now, I would like to hand over the platform to the chair.
Hello, can you hear me?
Yes, sir. Yes, sir. We can hear you.
Okay, thank you. Thank you. And I am Dr. Thomasutty Matthew, Associate Professor, Geetham University, Bangalore. And I am very happy to come as a chair for the invited talk in connection with the APSYM. And I would like to introduce today's speaker, who will be giving a talk on ultra-wideband antennas for diversified applications, a journey for a decade and future directions. And this will be delivered by Dr. Chinmoy Saha. He is an associate professor of Department of Avionics, Indian Institute of Space Science and Technology, Trivandrum. And he completed his PhD in radio physics and electronics from University of Calcutta in 2012. And he has visited several international universities of repute, like Royal Military College of Canada, the Queen's University, Canada, and he has in various capacities has collaborative projects with RMC Canada, Kingston, Ontario, and University of Alberta, etc. So he is a senior member of the IEEE and a life member of IET. He is the founding and current chairman of the IEEE MTT of Kerala chapter. And he has also received several awards from IEEE, and his current research interests include wireless power transfer, energy harvesting, channel modeling for WB, UWB and systems, microwave circuits, and so on. And with this, I would like to invite Dr. Chinmoy Saha to deliver his talk. Over to you, Dr. Saha. Dr. Saha.
Am I audible? Yeah. Okay. Can you hear me?
Yes, sir.
Okay. Thank you very much. To the session chair, Dr. Kutty from Geetham University, Bangalore. Before I start, let me place my humble submission to the organizing committee of APSYM, Antenna Propagation Symposium, which is happening for last 3 decades, starting its 1988. And APSYM has a different role. I mean, in our early career, because I remember still the dates during the early career of our PhD, used to come from Kolkata to Cochin, to present our article. And the way the organizers of APSYM are organizing this event for last many years, almost more than 3 decades, definitely deserves special applause. The way, with very simplicity and methodical way you do it, but ultimately it is very effective. It reminds me of some of the statement by a monk during my tenure at Ramakrishna Mission, that simple living and high thinking. So you don't have, those many gala dinners or some other things in the conferences, but you ensure it's an effective learning platform. I have attended this conference several times. I mean, several, platform as a PhD student, as a early career faculty member, and also probably now mid-career faculty member. So I congratulate the organizers to bearing this heritage and organizing this conference so nicely over the year. And also thanks for the nice introduction. This particular talk that I am going to have now for next 1 hour is basically an ultra-wideband antenna for diversified applications, where I'll be covering work which are mostly done by us. And when I was contacted by the organizers with Professor Das Krishna, Professor Ananda, and others, I was told that try to keep it in a little bit mode, not in the research mode. So I try to keep it in a little bit tutorial mode so that the beginners can also get an idea. As the title suggests, because it's a journey, mainly our journey and future directions, so it will involve different collaborations with my guide, of course, Professor Siddiqui, and then some part of the work was done at Royal Military College of Canada, and several students have also been involved in this particular journey. So let me move ahead. So this is a slide which normally I present in other podium. Probably it's not that much over here.
Hello, sir.
Yes.
Sir, can you switch on your video? That is not your talk. Is it possible to switch on your video?
Okay, just a minute. I have my video on from another device, from my mobile. Do you see me?
Okay, fine.
Yeah, because internet connection is not very stable, so I thought I'll have connectivity in two devices. Is it okay?
Yes, now it's okay. It was, the other one was me.
Yeah. Do you see me also through another device?
Okay.
Can you see me?
Yes, of course.
Okay, thank you. So this slide, to just have information about the institute. We started our journey in 2007 under the leadership of Dr. Kalam, the missile man of India, and later on became the president of India. So it's pretty close from the organizing place, the Cochin University there at the northern part of Kerala, where the extreme southern part of the Kerala. Only point I would like to mention over here, we have almost 1,000 scientists working at different centers of ISRO who are graduated from our institute. So, and being a part of Indian Space Mission, Department of Space, that's information that makes us really proud. So before I go into the agenda, just let me briefly talk about the research activities in our group. It can be dominantly divided into two categories: the printed antenna research, space antenna research, because we are part of the Department of Space, and also some of the new work that we have started into the area of millimeter wave and terahertz, and also wireless power transfer. So I'll just take another couple of minutes or so to give you some ideas about the activities that's happening in our group. We have done quite a bit of work on metamaterial inspired antennas and circuits. As you can see, different kind of structures, passive components, etc., filter, and then that has been deployed on different kind of antennas, the printed antennas, sometimes on some dielectric antennas also, and then some kind of antenna like for space applications, especially for feed horn, etc. We have deployed some of the technology over there. I'll be going a little bit in details because this is one of the points that I'll be discussing for ultra-wideband antennas applications, which is for cognitive radio. So this is the feature article in the Antenna Propagation magazine 2018, and it's a very nice for me to tell that this work was mainly contributed by one BTech students, and in addition with my PhD student who is now working at Space Application Center, Ahmedabad. So these I'll be going into detail, and in fact I'll be sharing a video clip while I'll be discussing dual reconfigurable antenna which can have cognitive radio applications. The same antenna can be used for notched reconfigurable applications as well as narrowband reconfigurable applications. So this is something which is very useful for some of the upcoming radios. So I'll be coming into that also. And then we have a dielectric resonator based wireless power transfer, which we have started off late. And today I go into the details of this, but this is something which is going to be very important and is coming in a big way, because the UVs, electronic vehicles, and some of the medical applications also, requires wireless power transfer, for example, recharging some of the embedded gadgets, embedded electronics inside our body for biomedical applications. So these are the two major applications which drives this particular market. And we also do some work on photoconductive antennas, which is for millimeter wave and terahertz applications. So with this, let me go into the today's agenda. Also, just this last slide on this part. So we do work with for satellite tracking applications, which is collaborated with different centers. So this is with National Remote Sensing Center, Hyderabad. So with this brief introduction, now let me go into the details of the presentation. I'll be introducing, the UWB technology, and then I'll be talking on the frequency notched multifunctional dual decoupled ultra-wideband antennas, and then I'll be coming to the cognitive radio applications. So when you talk about the ultra-wideband antennas, the first point that strikes us, why ultra-wideband? It is basically, as we know, the necessity is the mother of invention. So it is the communication technology and the demands. I mean, the communication becoming more and more data-centric. Antenna engineers needs to comply and to come up with antennas which will be supporting the different amount of bandwidth that is demanded. So these are different genre of antennas, starting from some of the ancient antennas like dipole, monopole, etc., and then log periodic, etc., Yagi antennas, and then printed antennas. And as you know, different candidates are having different amount of bandwidth. And when we talk about bandwidth, percentage bandwidth is defined by this, and then FU minus FL by FC. FC being the center frequency, then the maximum possible bandwidth will be less than 200%, because this equation would give you a maximum value when the FL is minimum. And FL minimum can't be 0, because 0 will be DC, and DC can't be radiated. So this is one of the point when you think about the ultra-wideband antennas, what is the maximum fractional or percentage bandwidth we can go? So this says that theoretically it can't touch 200%. And then coming to the modern applications, that cognitive radio multifunction applications and beyond. So two statistics, one done by IEEE, another survey was under the leadership of Professor Rappaport, says that the spectrum, which is normally dedicated for different communication systems to the primary users, are not efficiently utilized. So there are spectrums which are, primary users not utilizing the spectrum, which are called spectrum holes. So if these spectrum holes can be used efficiently, then we can have a better utilization efficiency, which in turn gives better capacity, better networking capacity, and so on and so forth. So this particular slide, as you can see, if we have enormous bandwidth and we have primary users, and then primary users not perpetually using the spectrum, then we have spectrum holes which are dynamic. If those spectrum holes can be used in a dynamic fashion, then you can actually enhance then you can effectively. Can you hear me? Hello?
Yes, sir.
Am I audible?
Sir, can you mute your mobile phone?
Maybe I disconnected. It is actually muted. It was muted. Yeah.
Oh.
Now it should. Is it okay now?
Yes,
Okay,
yes, yes.
sir. Okay.
Yeah. Yeah.
Please
So
get-
this is the point that I'm going to, like how the secondary users can be accommodated into the unused spectrum of the primary users. So let's start the journey, like application of ultra-wideband technology. As I told, the UWB bandwidth can be defined into different ways. So we can have, the percentage bandwidth, fractional bandwidth, and in 2002 the definition. So these are the typical 4 different definitions. The DARPA definition in 1990, if you have a fractional bandwidth more than 0.25 or 0.2 according to FCC 2003, then you can call your antenna ultra-wideband antenna. And if you operate around 6 gigahertz carrier frequency, then absolute bandwidth greater than 500 megahertz is also called ultra-wideband. And then this is the most widely used definition, that 3.1 to 10.6 gig is defined as the ultra-wideband. So these are of course the required features. Common features when you design the ultra-wideband antennas, you will be requiring for compact size, ease of integration, mechanical robustness, and some other things. And the application is enormous. Of course, some of the applications are ranging and localization, high-speed data link, wireless sensor network, UWB radar, and biomedical imaging. So if you want to really go into the UWB technology and UWB research, before you start the antenna research, you should also have some ideas regarding the signals and systems. So for the newcomers, I would say that you do a little bit of signal processing analysis and time domain understanding. So there are two different categories of UWB. So one is called IUWB or impulse UWB, which is without having any carrier. So it's like an unmodulated type of communication. And then you have multi-carrier UWB, which can have different categories. Like, so for these categories, UWB impulse radio, direct sequence spread spectrum, then OFDM, orthogonal frequency division multiplexing, and frequency hopping. Typically, the antenna engineers normally don't deal with this thing, but you need to have a good grip on these concepts, and because these are the points and these are the from which the UWB has developed. And then when you talk about the ultra-wideband, as you know, the time and frequency are related. So if you take the Fourier transform, then you move from time domain to frequency domain, and the relation is the reciprocal kind of relation. When a pulse is very narrow in time domain, it becomes very broad in the frequency domain. So from that perspective, what are the different kind of pulses that are very, very useful for ultra-wideband communication? That is also very important. So typically, these are the different genera of pulses which have been used. This is called the Gaussian pulse. That's how you define the Gaussian pulse. And then the second candidate is the first derivative of the Gaussian pulse, second derivative of the Gaussian pulse. This is many people call it monocycle pulse, and this is sinusoidally modulated, Gaussian pulse with a sinusoidal phase. So with these very brief statistics about the UWB signals and systems, let me come to the actual journey that I want to share. Ultra-wideband antennas, as I told, as the FCC definition is concerned, is 3.1 to 10.6 gig, and the advantages we have already mentioned. But the issue is, as a designer, the main point we have to consider is that within this ultra-wideband, there are quite a few narrowband services which are already there. So if we want to communicate in ultra-wideband signals without getting perturbed or without perturbing those narrowband communications, we need to ensure that the radiation level is below certain level. So that is called the frequency masking. And this particular table talk about the spectral mask that was imposed by FCC while releasing this ultra-wideband in 2002. So this is the the outdoor and indoor emission max level, and for different frequencies which has to be complied for real applications. So we come to various configurations of ultra-wideband antennas for different kind of applications. You will have plethora of articles. So I don't want to show all those things over here, but few candidates like spiral antennas, tinted monopole antennas, very popular. Some of the initial contributions was came from India, Professor K.P. Ray and Professor Girish Kumar. And then there are some tapered slat antennas, notched antennas, antipodal antennas also. And there is another, family of ultra-wideband antennas which started, initially US and Canada, and then now in India. Various groups have contributed, which is basically the hybrid antennas, which is combination of dielectric resonators and the typical rod type of monopole antennas. So this particular one, the left side diagram, is basically a patent by Professor Yahya Antar, with whom I have spent quite a bit of time. So this is ultra-wideband monopole dielectric resonator antenna. This is a patent in 2003, and then Professor Guha and many others have contributed immensely on this particular technology, the dielectric resonator based ultra-wideband antennas. But every candidate has certain pros and cons, so you have to deploy the antennas depending on the applications, and you have to choose a proper candidate as per your requirement. So with this, let me come to one of the applications, because the title says diversified applications. So the first point I would like to highlight is the ultra-wideband antennas for frequency notched application. I have talked on these on various forums, so probably for few of you it might be a bit of repetition. So as you know, within these 3.1 to 10.6 gig, there are a few narrowband services. These are two representative narrowband services, which is at 3.5 gig and 5.5 gig, having a bandwidth of 400 megahertz or 700 megahertz respectively. So the goal is to design antennas which won't be radiating at these particular frequencies. So as I said, if you go into the literature, there are different ways to design such antennas. You can have a basic ultra-wideband antenna, then you can use some notch filter or some kind of defect, some kind of perturbation on the radiator or on the ground plane to come up with frequency notched ultra-wideband antenna. But the way we designed and we developed this frequency notched ultra-wideband antenna was a little bit different. We just put a simple pair of resonator in the form of split ring resonators in the feed part of the antenna that doesn't part up, that doesn't tamper neither the feed line nor the that much of ground plane or the radiator, just by putting two tiny resonators, split ring resonators, which are called sub-wavelength resonator. Because of high distributed capacitance, you can get a frequency notch. And the beauty of this particular design, the design of the radiator and resonator is independent. So you can easily tailor the dimension of these resonators to get your frequency notch as at your desired frequency. So this is some of the fab prototype. As you can see over here, this is the basic circular monopole antenna, which is a CPW fed antenna. And on the back side, you have a couple of split ring resonators. The dimension and all is given. It depends on theoretical calculations, which involves the calculation of inductance and capacitance respectively for the resonator. And that's the point I said, that you can tailor the dimension and you can come to the specific design depending on your frequency of operation. So if those who are interested, to do some work in this particular area for calculation, there, I keep on getting quite a few mail in 17, 18, and so on and so forth. So we thought of having an appendix section in our latest article, so where we have clearly explained the calculations steps in the frequency, resonance frequency calculation of the resonator. So as I mentioned, the notch is obtained by the SRR's magnetic resonance. So these are the current distribution on the antenna, as you can see, at different frequencies. So this is the frequency at which the antenna doesn't radiate. That's because huge impedance mismatch by the split ring resonator. I don't want to use that material over here. Some people call it metamaterial antenna, but to us and with common sense, element, just a couple of element or so, can't be interpreted as a material. So it's a basically filtering action. Anyway, for other frequencies not around the notch frequency, I mean far away from the resonance frequency of the SRR, the antenna is radiates. That's because the SRR is transparent at these particular frequencies. So to understand the operation of this particular antenna using a GIF image, you can probably see the two animation on the left side without SRR, the antenna radiates at all frequency, whereas on the right side with SRR, the antenna can't radiate at the resonance frequency. That's being indicated by sudden the change of color. I mean, getting from reddish to completely bluish and sinking it. So that indicates non-radiation at that particular frequency. So this type of antenna radiation pattern measurement is very crucial because the tiny resonators are there, and then your antennas are also pretty small. So you have to ensure that you make sure there is no radiation from the feeds. Then perturbation, I mean the radiation pattern will be quite perturbed. Using ferrite rings and other kind of things around the feed line, you have to take the pattern. So these are the pattern at 3.1, 6, and 10 gigahertz for each plane and H plane respectively. So as I mentioned, around the radiator, as you can see, this is the 50 ohm feed line CPW antenna, fed antenna, and you put a ferrite ring so that because you have a transmitting horn from the other side which is illuminating this antenna. You want your antenna to be characterized, and you don't want the signal reflected from these feed lines to disturb your pattern. So this type of precise care has to be taken for measuring this type of antenna. And as you can see, the maximum gain versus frequency plot, it's pretty flat, and it drastically drops around the resonance frequency of the SRR, because that's what we intend for. Now, this was the first concept, like one of the unique designs where without any perturbation on the radiator, without putting defect slots, etc. on the radiator, we came up with a frequency notched ultra-wideband antenna, which has real applications. And then, of course, at that time, there were points like how can you make it dual band, triple band, and so on and so forth. So, as I mentioned, because it has a strong theoretical calculation and we don't use any perturbation on the radiator, so you can easily deploy a couple of resonators of different dimension to make it, multiple notch or anything else you want. So I'm not going into the details of that particular result, but as you can see, this particular idea of putting the resonator near the feed line, some people call it field antenna, is so unique. You can deploy it on varieties of antennas. So this is a Vivaldi type of antenna, exponentially tapered slot antenna, which is here is you have a microstrip and then you have a radial stub, and this is the slot. The slot is gradually tapered using an exponential profile. You have lambda by 4 radial stub over here and there also. So and not only one shape of the resonators, you can deploy different shapes. As an initial academic interest, we are using square SRR, hexagonal SRR, circular SRR, etc. And then we optimized and we know which one can be used for different geometries and different applications. So this is the uniqueness of the idea, and as I mentioned, this same idea can be deployed for designing the frequency notched horn antennas also. If you do without using an additional filter section, if you want to remove the adjacent bands and etc. while receiving data using satellite link or anything like that, because you basically receive very low level of power. I mean, definitely several negative of dBm. So there you can definitely deploy this kind of filtering structure on your feed horn, which finally sits on the focal plane of the reflector. And then, as I mentioned, the uniqueness of the present technique later on in 2018 TAP and 2017 MOTL, we demonstrated this idea by putting the resonator in this particular region at two configuration. In one case, we put it near the aperture. You have two planes over here. The dark color is basically the bottom metallization, and this brown color, which is the left side one, is the top metallization. We put the resonator here. In another configuration, you can put the resonator over here. So this is the excellent transition. This is the antipodal configuration, and then you have the microstrip kind of section over here, and then it becomes the coplanar strip line kind of thing, and here onward it gets tapered, and this is the radiating region. So you put with two different configuration, you get a very sharp notch, and as I said, it has a high theoretical correlation as far as the resonance frequency calculation is concerned. And the point that I mentioned, the design of the radiator and the resonators are independent, that still holds good over here. And then this is a particular design, which is an ultra-wideband tapered slot antenna for reduced cross-polar radiation. Antipodal antenna, as you know, is very convenient because you don't have to go for microstrip short line type of transition. In antipodal configuration, you are basically starting with a microstrip and then you are making it a coplanar strip, and finally you are tapering it out. But these two metallizations are on two different sides of the substrate. As a result, what happens is the electric field is skewed, and that skewed electric field creates an undesired vertical component of the electric field, which causes the cross-polar radiation. So if you want to have the antenna advantage intact and to remove the the disadvantage in the form of high cross-polar radiation, you need to have a different idea. So this is something which is called the balanced tapered slot antenna. So which is done by using an additional layer. So now you have another ground plane, you can say. So thereby you have the three metallization, one intermediate sandwich layer in between these two layers having same epsilon, and of course a little bit innovation and changes will be there in the antenna design. So now you can quickly understand from the the electric field profile of this one, that for when you have the normal configuration, the antipodal tapered slot configuration, you have your electric field from the signal line to the ground plane like this, and which has a horizontal component and undesired vertical component. So this is the guy which causes the cross polar radiation, and this just for demonstration you are using it. But when you are using at high frequency, if you want to see it at high frequency, because your TSA is like this, so high frequencies are radiated from this particular region, low frequencies are radiated from this particular region. So when you see the high frequencies, basically the separation between this top metallization and bottom metallization is very less. So here the vertical component is pretty significant. So at high frequency, these antenna will reduce, have a very significant cross-polar radiation, which in most of the practical applications can't be tolerated. But when you innovate this structure by balancing, and now you have one more metallization on the other side. So your electric field is going now like this and this. And as you see, the horizontal component are additive, vertical components are cancelling, these two are cancelling each other. So thereby you won't have any cross polarization. And that's true not only for low frequency, but also for the high frequency application. So that is the advantage. And as I mentioned and explained through some of the annotations, probably you can follow from here also, from the animated electric field pattern. So you can see for antipodal configuration, your electric field is like this, which is skewed, and that skewedness will be more, and it will have more cross pole at the high frequency side. And when you balance the structure, your electric field is having two component, two different orientations. So both of them will be adding the horizontal components, and the vertical component will be cancelled. So, and that's true for low frequency as well as high frequency application. So this is the interesting result as far as the theoretical understanding and the ideas are concerned. So this is the normal antipodal tapered slot antenna, as you can see at some of the frequencies, which is you can see the separation between copole and crosspole is not that high, especially at high frequency it will be severe. But when you balance the structure, balanced antipodal tapered slot antenna, both with simulated results and measured results, you can see there is a very good, around more than 30 dB cross-polar separation towards the main radiation, that is towards the axis of the antenna, which is the axis of the slot. So this is some of the applications towards the the notch applications, frequency notch applications on different types of ultra-wideband antennas. Now let me take you to another interesting applications, which is for multifunctional operation of the antenna. What is the term multifunctional? We have heard of reconfigurable antennas a lot, depending on the change of the pattern or change of the frequency, polarization, or combination. We can have antenna reconfiguration. We call it frequency reconfigurable, polarization reconfigurable, pattern reconfigurable, etc. And then you have to deploy different mechanisms to achieve a reconfiguration. Sometimes it can be electrical or physical or optical or material change based, and for which you have to deploy different kinds of switches or mechanical actuation or photoconductive switches, etc. to realize this kind of reconfigurable antennas. Multifunctional antenna, as the term multifunctional says, is quite close to it, but here the functionality is in terms of the application. So if you follow this particular flow chart, the block diagram over here, so the way we have designed a single antenna governing three different operations is something like this. You have a planar ultra-wideband circular monopole antenna, as I was explaining previously, and you have a split ring resonators which is loaded beneath the feed line, and then that antenna becomes a frequency notched ultra-wideband antenna. And interestingly, when that antenna is further augmented with a pair of switches in terms of a couple of shunt wires, which practically will be pin diode or MEM switches, etc., then the antenna becomes a narrowband antenna. So to make it very simple, we have used like a Boolean table over here. So configuration A, which is governing the narrowband antenna, and then configuration B is the notched ultra-wideband antenna. Configuration C, where you basically try to close this particular gap of the switches, thereby the SRR becomes CRR, you revoke the ultra-wideband response. So this was the first time an antenna, a single antenna governing three different responses was reported, and this is our initial experiment. The implication of this particular result is enormous, because you are having an antenna which can govern you the ultra-wideband operation, which can give you narrowband operation also. And by some means, if you can make that operation, that is the reconfiguration operation, tunable, that would be a fantastic candidate for some of the modern radio, like cognitive radio antennas. I'll be coming a little bit in more detail of that. So this is what the design says. Like you have over here, and you have pair of switches over here, where the switches will be ultimately pin diodes, etc. I'll be coming to. And this is the fabricated prototype. Initially, we just use the copper switches in the fabrication step itself, so it's a kind of a closed switch configuration. And another prototype you can develop with open switch configuration. So you see the beautiful characteristics of the antenna. Same antenna gives you two different responses. In one case, it is a notched ultra-wideband antenna. As you can see, this case is a notched wideband antenna. And in the other case is basically you have a narrowband antenna. Same antenna with switch on and off condition. You are actuating and deactivating the switches and invoking two different frequency characteristics. Not only that, this is from S11 response. Same thing is complied from the gain response of the antenna. As you can see over frequency, the gain of the narrowband configuration is pretty low at all frequency excepting at the narrowband frequency, whereas for the other case it is a notched antenna, so that's why its gain drastically falls around this design frequency, which is around 6.5 gigahertz. So now it's a dual complementary antenna, of course, but I can't claim that it can be used for cognitive radio or something like that, because here we don't have the frequency scanning for the narrowband. So to do that, you have to have some other mechanism. So as a proof of concept, theoretical proof of concept, I would rather say, we change the dimension of the SRR, and using the dimension, changing the dimension of the SRR, you can show that a good amount of frequency tunability in the narrowband is achievable. Now the question is, once you fabricate a device, how do you do that? You can't do that, right? So it's that's why I said it's a theoretical understanding that, but if you electrically can change the dimension of the resonator, you can tune the narrowband operation. And then later on we showed that by replacing that SRR by varactor loaded SRR, that is thanks to the tuning of the varactor and changing the bias voltage of the varactor, you can get this frequency reconfigurable narrowband operation also. And then I'll be coming to the details of that particular one. And this particular result is basically the time domain response. As you can see over here, this is the group delay of the antenna for two different configurations. That's for the notch configuration, you have a pretty flat group delay excepting at the notch frequency. Whereas for the other configuration, you have a very flat, almost horizontal kind of thing. And this indicates the two different operation of the antenna from a different perspective, time domain measured data. And this is another kind of way to understand the performance of the antenna, which is in terms of the pointing vector as a function of frequency and as a function of distance. In one case, as you can see from the the rectangular contour plot, this color indicates the magnitude of the pointing vector. So this is the notch actually. So this particular frequency, which is around 6.3 gigahertz over here, that indicates the notch. Whereas in the second case, this particular, you have intense pointing vector only at this particular frequency, which is around the same frequency, 6.3 gigahertz. So these also indicates the complementary response of the same antenna, and that's also gives you the similar kind of measured pattern. So this is the experimental part, because we are deploying some switches in this particular case. So these switches are basically the the RF switches, so which are basically, it can be pin diodes or name switches or etc. Initially, we did our experiment with a pair of commercial pin diodes, and before doing this particular switches getting integrated on the antenna, we did it just for a filter section. And this experiment was done at RMC several times, of course, because we have deployed this idea on several type of antennas. So this is initially a filter section, and you have a pair of diodes over here, and this is the typical measurement, because you have it's basically S1 measurement going to port 1 and port 2 respectively, and this is the bias for the pin diodes. And real arrangement, when you connect it with the antenna, you have the RF and you have the DC, and then you use the bias key to do the initial experiment. And as you can see from the measured response, the impedance response as well as the gain response of the antenna, in one case as you desired, you get a notched operation. In the other case, when the diode is on, you get a narrowband response. So the same antenna gives you complementary responses, and that's verified experimentally. And as you can see over here, these are the commercial specification of the pin diodes integrated on the antenna. I probably will try to show if it runs. Probably it will run. Let me see. So this is a interesting video which shows the notched and narrowband operation getting dynamically changed depending on the bias. So you see, that's what I wanted to show. that you see. This is currently, it is showing a notch kind of operation. This is the S11 response. In the second case, when the switch is on, you are getting a narrowband kind of response. So we tried to capture. So these were the initial experiment where there was a little bit of problem, but later on we fine-tuned it, and we took care of these higher orders, etc. And we verified this particular performance using the experimental results. So frequency tunable operation, because I mentioned that this is happening at static frequency, two different functionalities. One is the notched, another is the narrowband functionality. So by changing the dimension, you can of course show that in the function works. But as I said, practically it has to be done by not changing the actual dimension, but doing it electrically. So I'll be coming to that part pretty soon. But before that, just wanted to mention that this concept is so generic and it can be applied on various type of antennas. You see, here I was showing on a circular monopole antenna. Now you know the tapered slot antenna is also a very good candidate. And to keep the CPW configuration readily applicable, we designed a CPW fed tapered slot antenna. There is some engineering involved in the feed region over here. So this is the CPW section, and then this is the matching section. Actually, two slots are ultimately converged into a single slot. So this is the radiator and this is the resonator. And these two red lines, red points are indicating the switches. And with switch on and off condition, the same kind of response with antenna 1, antenna 2, and antenna 3, giving the ultra-wideband, notched, and narrowband response is proven using the similar kind of concepts, and that is verified using the the surface current plot at different frequencies. Only at this particular frequency, which is the notched antenna, is not radiating. So you see the it is not excited, but at all other frequencies in 4 gig, 6 gig, 8 gig, and so on and so forth, the antenna is pretty much excited. So another application that I would like to highlight is UWB antennas for the cognitive radio applications, because that's what I initially talked about, that it can have so much of applications in the modern communication scenarios. So before I go into that particular part, let me take another couple of minutes or so to introduce the cognitive system. If you see the Oxford Dictionary, or if you just want to know what is the meaning of cognitive, the term cognition and cognitive means it's basically intelligence that is gathered from the environment. So if a system is intelligent system, that means it has a high cognition, means the system adapts itself from the environment. So according to the Hacking, this is the definition of cognitive radio. Like, it's an intelligent wireless communication system that is aware of its surrounding and uses the methodology of underlying understanding by building to learn from the environment, adapt its internal state of statistical variation. Anyway, so it's basically the point from an antenna engineer's perspective I want to highlight is, as I mentioned earlier, basically sensing, learning, and reasoning, or it is sometimes called the famous Odal cycle, that is the observe, decide, act, and learn. So employing multiple radiating elements on a common substrate, that is the idea why I'll be coming to. And employing single radiating elements is another idea which we have developed. This particular figure we have taken from our book. As I was mentioning earlier, the multifunctional antennas and the spectrum holes which are present, as the output of two different surveys, IEEE survey and a survey by Rappaport and few other groups, it shows the primary users are not utilizing the spectrum effectively, which causes basically underutilization of the spectrum. And there are so many attempts to enhance the capacity of the network, and the new things like MIMO, massive MIMO, etc. are coming. That's of course very good. But along with that, if this idea of spectrum utilization efficiency enhancement can be integrated, that would be great. So this is an idea where you have ultra-wideband antenna, and then you have the tuning arrangement. So you have sensing antenna, which will be giving you the information regarding the available spectrum or the ideal spectrum. And as soon as you get an information regarding the ideal spectrum, you have to have a mechanism to radiate at that particular frequency, which can be done by having multiple radiators, and this particular section is basically rotatable. Professor Christodoulou has conceptualized this idea initially, like multiple radiators, and at a time one of them will be actuated. So these are some of the ideas, as I was telling, the primary users and secondary users. So secondary users are basically opportunistic users, which has to use the ideal spectrum properly. So this is one of the scenario where the secondary users will be using the holes or the spectrum ideal spectrums, which is called the spectrum interleaved scenario. Another scenario is the secondary user can utilize the entire user, but they have to radiate below certain level, below the allowed interference level. So this is called the spectrum underlay scenario. So this is the very basic idea, and the antenna requirement for that is very crucial, because you have to have a sensing antenna which will be sensing the ultra-wideband signals and will give you an information regarding the ideal spectrum, and you have to ensure that secondary users are capable to radiate around those ideal spectra. So as an antenna engineer, what is the basic requirement to come up to a cognitive radio technology? So you need basically a system like this. You need to have the sensing ultra-wideband antenna, because you need to see the whole spectrum, and then depending on where you have the hole, you have to communicate. So that is the requirement, reconfigurable frequency reconfigurable antenna. These are some of the reported structures by Professor Christodoulou mainly, and Professor Peter Hall has also contributed in this particular point. Like, as you can see, this is an elliptical monopole antenna, which is the ultra-wideband sensing antenna, and then there are quite a few number of radiators, and this particular section is rotatable, and this rotation is actuated by this particular motorized operation over here. There is a motor sitting on the back side, and at a time one of these radiating elements will be connected with the feed line, and thereby you make sure that this antenna is frequency configurable antenna, because those are designed in that way, and this antenna will be basically giving you the information regarding the ideal spectrum. So if you go and dig the literature, you will see quite a few interesting design. So this is another idea where you have depending on the status of these switches, as you can see this particular structure, it's basically a circular monopole antenna, which I was talking about earlier also. Only difference is this one is microstrip fed, no problem, but the main innovation is to having some switches and some filtering action over here. So depending on the status of these switches, D2, D3, D4, D5, etc., and then you can either actuate this line or this line or this line, and thereby these are basically like the filter section. So this same antenna can give different kind of impedance responses and similar kind of radiation response, because whatever reconfiguration is happening, that is at the feed region. And then these are some other arrangements where you have the optically controllable operation and optical switches, of course, but these are a little bit complicated arrangement, because to actuate these switches you need the the fibers and the optical source, etc., to actuate the switches. But these are some of the reported articles, so all of them might not be equally applicable as far as the the design and the applications are concerned. But I'll take you to some of our journey towards this now, because I talked about the notched antennas earlier. Now this is very interesting. We talked about an antenna which is loaded with the resonator, and this gives you the frequency notched ultra-wideband response. Now if you have a couple of switches over here, as you can see probably here, with these two switches actuated, you get a narrowband response. Now if you can control the status of the switches, you can have two operations toggled between the two complementary states, that is the notch state and the narrowband state. So this is the idea we wanted to deploy and propose some of the antennas which will be very, very useful for cognitive radio applications. So these are the arrangement. As you can see, there are different pair of resonators of different dimensions and different switches. By actuating a pair of switches at a time, you can actually provide triple notch response and triple narrowband response, and by choosing the combination properly, you can actually operate or choose different frequency of operation, that is both for narrowband as well as the frequency band. So it is of course reconfigurable at 3 different bands, but it's not smoothly reconfigurable as of now. So further changes will be needed. So I'll be coming to that particular part. Before that, let me show you another interesting piece of work. This is the extension of the previous concept. You have switches, you have the resonators, but to ensure that the feed line is not getting elongated that much, another pair of resonators are loaded on a superstate. So this is the superstate. On this particular superstate, you have another pair of resonators. So thereby you have a couple of resonators below the substrate and couple of resonators above the substrate. And I will be skipping this particular equivalent circuit modeling, but for the beginners it's very important. Simulation, measurement, theoretical calculation is one thing, but circuit simulation sometimes is very effective. So this is the equivalent circuit of this antenna along with the input termination and the antenna impedance, which is taken from the EM simulation, of course, and the equivalent circuit of the SRR side, the top side and bottom side. Due to the magnetic symmetry, this is basically the 50% equivalent circuit. Another 50% equivalent circuit is there, which is in parallel with this. Anyway, so this is an excellent candidate, because here also, depending on the combination of the switches, status of the switches, and those resonator dimensions, etc., you can achieve very interesting antenna response. So this is the continuation of this concept to design a frequency agile antenna, where this particular part is we are using a mechanical arrangement to make it translational, to actuate a translational motion along with the electronic switching. So it's a combined idea to design a frequency agile antenna. What happens is, depending on the position of the pair of SRRs, which are sitting just below the, above the CPW line, and getting translated by this rack and pinion arrangement, which was ingeniously designed by that particular BTech student. Anyway, I'll be coming to that. So you can actually make this antenna continuously tunable over 3 different bands, and by using the switches and this motorized rotation. So this is the superstrate which is loaded on the antenna, and then we can make it movable along these by the motorized rotation. So this is the overall arrangement of the antenna, mechanically tunable multifunctional antenna. You have copper strip over here. On the back side, on top of that, you have the superstrate, and this is the the actuation to the Arduino board, Arduino microcontroller, and this entire calculation, the teeth size, the periodicity, and the coding, where to stop, after how many turns it will stop, so that at a time either of those 2 resonators are excited. So all those things are very involved work in this particular. So this is the overall setup before we went for the experiment. As you can see, the overall this is going to the network analyzer, of course, and so the basic information, of course, the motor, the Arduino board, and probably these will be very interesting. You will see the whole picture from this. The guy who designed this, realized this, is Rajesh, along with my PhD student Latif. So you can see. So we have a substrate. We have a superstrate along on top of the antenna substrate, and this is made movable using that switches. And as you can see, in real time, depending on the position of this, you can control the resonance frequency of the SRR. So this is for one of the configuration. You are seeing the tunable notches. For the another configuration, we got the tunable narrowband response. So this is the summary of this particular work, which is a single antenna. Then we have superstrate, we have switches. Switches can be on and off. Then you can have frequency notched ultra-wideband antenna. You can have it F1, F2, and you can have narrowband operations also at the same frequency of F1, F2, and F3. So this is a combined electronic and mechanical reconfiguration, and then we name this as mechanically tunable ultra-wideband notched and narrowband reconfigurable antenna. And this till now, whatever I have told, there we are having different antenna functionalities, but not the continuous tunability. So this is the last leg of the work for this antenna design for cognitive radio applications. So these we have shown for a Vivaldi antenna. As you can see, this is also an exponentially tapered slot Vivaldi type of antenna. Here, the feeding mechanism was used was the microstrip, and microstrip to slot line transition is there, as you can see. And since the number of SRRs are double for CPW feeding, and then the overall electronic biasing and etc. will be very, very complicated for two SRRs. So we prefer the microstrip configuration. So three different SRRs, varactor loaded SRRs are there. So varactor diodes are embedded in this particular position between the inner ring and outer ring. So what it does is, by changing the bias voltage, you are effectively changing the resonance frequency of this particular varactor diode. So this is the theoretical obtained frequency. It involves quite a few steps. So here is the bias voltage, and C1, C2, CG are the different capacitances which are related to the split ring resonators inherent capacitances. And then you have two different configurations for these also. This because in one case there will be another switch will be connecting the two sides of the slot lines, so that we can make it on and off. And this is the performance of the antenna for two different configurations. So for the varying bias voltage or effective change of the capacitance, in this case, as you can see, there is a continuous tunable narrowband operation, NB1, NB2, NB3, because there are three different pairs of the three different SRRs, and all of them are varactor loaded. So by these, you can effectively achieve a very good, almost an octave bandwidth from 3.5 to 7 gig. And same thing for narrowband configuration. There are a bit of loss at this particular site because the SRRs are very tiny, and doing these experiments is also very critical. Anyway, as you can see from here, that for the narrowband also, you can, this is for the other case, this is simulated response, and this is the measured response for the notch case. And as you can see, for the narrowband operation, continuously tunable from this gigahertz. For each of them, almost 1 gigahertz tunable bandwidth you are getting. And this particular antenna we tested 2 times because the initial result was not very encouraging. We tested at RMC and then at Space Application Center Ahmedabad also. So these are the work that I wanted to present in connection with the ultra-wideband antennas and its diversified applications. So we have used the pin diodes, varactor diodes. For some of the other work, we have deploying the RF main switches also, because depending on the application, sometimes you need to have a short response time. The switch actuation should be very fast, and the other point is like power consumption and then the parasitics, etc. So depending on that, you have to have a clear idea which switches can be applied in different scenarios. For one of the other applications, we use the cantilever-based RF MEMS also, but that's I'm not going to show over here. So this is just a comparative statement of different kind of switches that can be used. So with this, I want to conclude the talk with acknowledgements to different centers and universities and DOS centers, of course. And even though I presented the work is, it's a long work. Almost for a decade, as I mentioned, and several students have been involved with this work. PhD students have been seriously involved along with MTech and PhD students, and some of them are working at ISRO and some of the other universities also. For example, this is one of the guys who was very much involved in this design. Rajesh is at Pure Rao Satellite Center, and then Utkarsh is currently working with Professor Yahya Antar for his masters, and then some of them are at different ISRO centers. So quite a few students have been involved with this work. So this was kind of tried to make it tutorial, but probably I covered a bit of more horizon also. So that's why I would rather encourage the young students to see some of our published article on this particular area. So some of the IEEE journals, transactions letters, etc. And finally, in last year, with request from Taylor and Francis and support from Professor Siddiqui and Professor Antar, we came up with this particular book. So there you get a lot of consolidated information, multifunctional ultra-wideband antennas. So with this, I conclude my talk with sincere acknowledgements to all the bodies, the DST and my own institute, and of course ISRO, KCRB, from which we get projects, grants, etc. And also IEEE fronts, I can conclude this particular tab with sincere thanks and with an announcement regarding some provisions that is there in my group at IIS Trivandrum, and this is the book I was talking about. Incidentally, we have another book which is on basically teaching on the basic electronics principle and applications. So with this, I conclude. I'll be very happy to take a few queries. Thank you very much.
Okay, thank you, Dr. Saha, for a very nice and interesting presentation. And any questions? So, coming to your that mechanically some antennas that you are the resonance change the resonance you are mechanically moving. That
Yeah.
my question is that whether it will become more complex. That what are the applications that you can that type of antennas have you do you find any applications for that?
Yeah, it's not complex actually, depending on the application. So this can be, of course, not be used as a handheld devices or something like that. If you see the literature, then there is the concept of combined reconfiguration using the electronic switching and mechanical actuation. So this, because the motor is a very tiny motor, it's a 10-gram servo motor. It's not that complicated actually. But as an academic interest we do, but such articles are there, and for some kind of cognitive radio base station applications, this can have application because it's not that robust, not heavy. It's a 10-gram servo motor.
I think there is no question, only one comment. That is excellent work done by Chinmoy, Saha and team, and well presented. And exactly starting from the very basic concepts of antennas, and you have covered a wide spectrum of UWB antennas to coming to the state of the art antennas. Okay, and I am sure that it will be definitely it will benefit the researchers, the young researchers, and the PG students who are attending this conference will be definitely they will be getting benefited. And on behalf of the organizing committee, I would like to thank you for this very interesting and very interesting and knowledgeable presentation. Thank you very much, Dr. Saha, for your presentation. Thank you.
Thank you very much, Professor Matthew. And I am also, as I said at the beginning, I feel like I'm part of APSYM sitting in Kerala. And I have been involved with APSYM in various capacities earlier also. I mean, as starting from my PhD student and today as an invited speaker, I have a very special place in my heart for APSYM. Thank you very much to all of you. Thank you.
Thank you, sir. We are extremely thankful for you, sir, for sharing your deep knowledge about ultra-wideband antennas for diversified applications. Your session was full of enthusiasm and knowledge. Thank you, sir. I would like to thank Dr. Thomas Matthew for also sparing your valuable time with us. Thank you very much, sir.
Thank you.
Now, you're welcome. Now it's time for a tea break. We will resume here at 6 p.m. Thank you.
Thank you all.